All right. Good afternoon, everybody. Thanks for coming all the way to this room. I don't know where on campus you're located. It's a different spot. I'm glad you all found it. Before I introduce the speaker, there's a sign-in sheet, so please put your name and details on there, especially if you got food. So today it's a great pleasure to introduce Marek Kirs, who is a microbiologist in the Water Resources Research Center. His research focuses on microbial water quality and the impact on public health issues. He received his Bachelor of Science from Tartu University in Estonia, a Master of Science with distinction from the University of Edinburgh in the UK, his PhD from the University of Rhode Island, and the postdoc at the University of North Carolina. So he's been moving around quite a bit, and he's now been here in Hawaii for 7 years. And he's going to share some of his work that he's done here with us today. So Marek, the floor is yours.
Thank you everybody for coming, and I'm really glad to see so many people. It's going to be quick because I tend to speak very, very fast, so I try to slow down today. I have just 80 slides to cover, so it's going to be easy. And yeah, let's start it. So first of all, it's not really my work only, it's a lot of people who have been working with, and my mentors, my collaborators and students who have contributed these studies. And yeah, and first of all, also I'm really sorry if there are many people who are really knowledgeable about microbiology here in this room and virology. It's really basic talk, okay? It's not like deep microbiology talk. And I need to re-emphasize some of the things at the beginning, like the kind of first 10 slides to kind of get everybody to the same page. So why water quality matters? So there are two concerns. One is the human health concern, and another one is the environmental impact, the habitat degradation. And what is important on these studies, we all know that there is also the relationship between the environmental degradation and of course humans. Who cares? It costs a lot of money. So there are some estimates like 12 billion per year, plus minus 50% from 2003 is losses to the swimming and bathing related illnesses in polluted coastal waters for worldwide, and 2.2 to 3.7 billion for US, which is a more recent study. Yeah. So what and why we measure? So there is a lot of pathogen in the water. It's actually not so much, but there is quite a bit of different pathogens. And so to test for all these different pathogens is just tedious, difficult, and time consuming. So instead of pathogens, we use and measure indicator bacteria or microbial indicators. And the good question is really, what do they really indicate? Are they fecal indicators? Are they pathogen indicators? Are we trying to indicate how effective is our treatment? So it's all different questions. And purpose determines what indicators we actually use. And I tend to use two words, indicator bacteria and indicator organism. Usually I use indicator bacteria when I talk just about bacteria, and organism when I need to use coliphage, but I understand the phage is a question if it's really organism or not, but it's better to refer to it as indicator organism, I guess. So ideal indicator bacterium, it should be for recreational water quality. It should be present whenever the enteric pathogens are present. And it should be ideally useful for different types of water, in fresh water and indoor water. The organism should have longer survival time than hardest enteric pathogens. It should not grow outside the host. And testing should be simple for the labs. At least that's the ideally it should be. And really important is that the density of indicator organisms should have some direct relationship to the degree of fecal pollution, including the related health risks. So it should be based on the health risk if you're doing recreational water quality. And none of the indicator bacteria really well fits that requirement. So here are some indicator bacteria people have been using. So this total coliforms, fecal coliforms, Escherichia coli, Enterococci. For recreational water, we use last two, Escherichia coli and Enterococci. And yes, it's just a basic slide here, cartoon, that Escherichia coli is part of the fecal coliforms, and this is part of the total coliforms. Not drawn by size, but and has no taxonomic relevance, but yeah. And the problems with these ones is regrowth in aquatic and soil environments, regrowth in distribution water when we are talking about drinking water, and And if we have this regrowth, then it's not really indicative anymore of the health risk or threat. And there is no relationship between the bacteria and protozoa and viruses or environmental pathogens. And E. coli die-off is rapid in marine environments. That's just a fun fact. Not fun fact, but just. And some alternative microbial indicators, the bird alternatives kind of, I'm not sure if it's good to use it, but for example, qualifiers are actually used in drinking water programs. And so F plus and somatic qualifiers, here are some of them on the picture. Warming plaques, they are good proxy for viruses, at least that's current thinking, I think, is mostly. And but the problem is that, for example, qualifiers concentrations are relatively low in sewage, and methods are actually quite tedious, especially if you do it by cultivation. And Clostridium perfringens is here alternative. It's obligate anaerobic, cannot grow outside the host. It forms spores, but it forms spores that can survive long periods of time. And yeah, some people are criticizing this method, actually, MCP media, that it's not very conclusive. We have actually tested these colonies, and the false positive rate is at approximately 6% that actually noticed this also for enterococci test for, I think, from EPA. So it's 93%. We are kind of confident about our count, so I won't criticize the method. So here is, I don't have time to cover all this slide, but what I want to say is that it's a history of a Clean Water Act kind of some ways, and EPA implements Clean Water Act through a variety of programs. And what is important is really that EPA develops recreational water quality criteria, and states develops based on this criteria their own standards that must be as protective as criteria. So, and yeah, so critical, the most important part here is that states can use alternative indicators, but must demonstrate similar level of protection. So it's really important to show that health risk associated with this indicator criteria is same. So these are the recreational water quality criteria from 2012. These are the EPA recommendations. So what is important is the illness rate. So I said again, I repeat again, it's really important that it needs to be based on the measured health risk. So illness rate 36 per 100,000 or 32 per 1,000. The color is just different numbers. So there are standards for freshwater and marine water. In freshwater, you can use enterococci or E. coli. In marine water, you use only enterococci because E. coli doesn't like much salt water, as I said. And but it's important to know that these numbers have been delivered from epidemiological studies, which is superb and really great. But usually the situation is the fishes that have been used for these studies have been all contaminated by point source or by sewage, really. So that's what has been behind the studies. And so recreational water quality regulations, so this criteria is also important. It has many uses. So it's used to, first, one of the uses is there are water quality-based influence limits for NPDES permits. Then 303 listing, identify water bodies that are impaired and threatened, that needs to be fixed. So fixing them like using the maximum daily loads to kind of minimize the contamination inputs into the streams or lakes. And lastly, fourth is for pitch notification programs. So this is where I'm actually going to concentrate, but I just want to say that that's one of the, it's just one of the areas where water quality criteria actually applied for. And so Hawaii regulations for pitch notifications are based on enterococci, okay? And the limit is 130 coloniform unit per 100 milliliter. That was in previous slide as well. We used to use Clostridium perfringens, which is great, but it's not longer used for pitch notification, which is surprising, but I try to stay positive. I kind of see my failure, kind of this one, not being able to champion this one here in Hawaii, but currently we do everything based on the enterococci. And you have probably seen much higher number of pitch notifications is constant in TV, and current situation is kind of extremely satisfactory, and I'll explain why. But it gives bad reputation to Hawaii because you go and see the signs quite often now, and too frequent notifications can be ignored. And if you're ignoring something, what if something truly that you need to worry about is there. So this is Toheni State Beach. There are surface black dots that I accidentally happened on one weekend on that beach. And I talked to this surface because I saw the signs and they said, don't care. Every time it rains, they put the sign out and we just go. We just don't care. So now we get to the topic. So challenge one, so the growth of indicator bacteria in Hawaii soil. So I'll show you what it is. So it's nothing new, and this has been repeated all over and over for 25 plus years. Dr. Fujioka and others have shown the high concentration of Enterogocki and as well as E. coli and total coliforms is present in Hawaii soils. So it's not a theory or a hypothesis, it's just a fact. So there is nothing to argue about that. So there is high levels of Enterogocki. And it's not surprising because all indicator bacteria that I showed you, is E. coli, Enterogocki, total coliforms, they all grow in aerobic and anaerobic conditions. And we have warm weather year round. So every time it rains, the levels of indicator bacteria in streams exceed up to 1,000-fold water quality standards that we have, 35 or 130, whichever you use. And it's close to what found in sewage. The sewage is usually 10 to the 5. So if you have 10,000 in your stream water, which can happen, you're just a little bit less than raw sewage in your Enterogocki concentrations. And it impacts our water quality on the beaches. So this, of course, the Enterogocki will end up on the coastal waters, and you will see high counts. But what does it truly mean? I don't really know, and I don't know that anybody knows what the health risk truly is associated with these levels. So we collected. That was a drinking water project, but I'm just showing you a little bit. First, I start with this data. We had 37 wells, but we collected soil samples, around 34 of them. And these wells are all fenced, so there is no public access, so they're quite protected. Sure, the animals can access this one, but all samples are positive for total coliforms and Enterogocki. And geometric mean of concentration of both organisms were quite high. So this is per gram of soils. I just took, this is 1 gram, okay? This is very small volumes. If you do 100 grams, like 100 milliliter water sample, just amplify this number by 100. And so these are the concentrations that we see in these samples. And what else is important? Actually, C. perfringens was also quite relevant in these samples, which is a concern. So we had also 2 students over last summer, and one of the students was looking at Adam Cannon. He was looking on soil samples. He was looking at soils and actually microbes in the soils and differences between the microbial communities under the native soils and non-native soils. But one of the things he did, he also measured the Enterogocki concentrations, and again, high levels of Enterogocki per gram of soil and E. coli, total coliforms, but also found total coliforms. What is good, probably what might be interesting, is that no coliforms were actually detected really on those samples, soil samples. Or F plus that was present. Okay, yeah. So this is kind of good sign, and it's not only in soils; it also rains down from the vegetation. So this is another student, Annette Ludwig from Guam, and they both worked really hard. I have never seen so hard-working students. They just run me. I need to be in the lab like 7:30 before they came to kind of keep up with them, and they really run me. Anyway. They did a lot of work. They did a lot of interesting analysis. But anyway, so these are averages for 5 samples that they saw that Enterogocki, total coliforms, E. coli, again, really, really high numbers, but not so much of coliphages. So we had trays like that under the trees, and we collected rainwater, and it actually rains a lot. So this was like, you can see actually, this is probably 2 nights, and it's half or over half full of trays. So we autoclave them and pull them out. But surely some animals or anything could kind of crawl in, so it wasn't the ideal setup, but it was next to Lion Arboretum. So anyway, it rains down from the trees as well, so that's the point. So every time it rains, there is high levels of Enterogocki coming in our streams. And does it impact our water quality? We don't know. And what do these concentrations mean? We really don't know. And managing just watersheds based on the concentration of Enterogocki is kind of futile effort, I think. So you can just your bank there and throw it. You can definitely see, if you know that you have sewage break, you probably can identify that in your stream because the numbers should go up if 10 to the 5 is coming in. But you can get them down, but you can never meet the recreational water quality criteria in our streams. That's what I strongly believe. So what we can do about it? So there is two options. So epidemiological studies I did is a golden standard. And what they do is they, okay, I have that. So what they do is they measure illness rates among the swimmers and enterovac concentration. So I think I pointed illness rate versus illness, okay? And each of these points is actually a lot of studies because the risk is based on the 32 or 35 per 1,000. And so you need to question a lot of people. So it's quite hard to get these numbers. So this is a combination of many studies from the 80s and from the last decade that EPA did to come up with a new water quality criteria. So that's a good option, but it's not going to happen in Hawaii because yes, we have several beaches where we have a lot of padders, but the problem is when you collect water samples, it's very hard to find the one with the high concentrations. Some famous oceanographer said that give me a ship of iron and I give you ice slates. I would say give me a couple of classes and Manoa students and to drop in the Hawaii Canal, I'll give you the water quality standards. Yeah, so it's not going to happen. So alternative option is health risk modeling using quantitative microbial risk assessment. So how this one works is identifies health risk based on the reference pathogens. So you have a set of pathogens, and often the studies claim that these pathogens are responsible for 97 or 99% of recreational water quality illnesses. And then we use dose response relationship, which has been determined by other studies, which is probably the weakest actually aspect of this one, of this approach. But this is really the only way right now how you can do something changing in Hawaii. Anyway, so you measure these reference pathogens and you measure your indicators, and then you develop relationship. Then you can identify which of these indicators actually relates to the health risk, and determine also concentration, which would be protective, like 36 out from 1,000 based on these calculations. But it's really based on the concentration of pathogens. And the detailed methods have been promised long time ago, like not long time, 2012, but we are still waiting from them. EPA actually supposed to make it available, but this document is not yet out. And yeah, it has all these 4 steps, which is all good. So we have currently a study that we're doing with these organizations, Stanford University. It has been done here before, the QMRI, but it was Yao and Beam in 2011 who did a study here. But it kind of went unnoticed, I will say, because I don't still understand why we can't use Clostridium perfringens, because the study clearly showed that C. perfringens correlates very well with health risk in Hawaii compared to the enterovac. Anyway, so we're working with these organizations, and we're trying this summer to run another study similar to the one. So that's what I do. I copy what everybody else in mainland. That's my life. And it's not exciting new research, but we desperately need it. So that's what's behind of it. And we assess, yeah. So we want to kind of support current or development of alternative recreational water criteria in Hawaii. And it's very policy focused. Hopefully we can cause policy change back to the alternatives. But of course, I can't say that because we don't really know what the outcome of the study is and so on. And yeah, so that's about that. And this is the sites that we're planning to study. I know it's kind of bad to talk about what you're planning to do. So these are the different islands that we're planning, and these are the indicator bacteria which we concentrate on reference pathogens. I'm still not sure about all the reference pathogens. Maybe we should have some. This list is kind of based on the combination of Yao and the SCORP study that was recently published. But I'm still thinking about maybe bringing like some Cryptosporidium and Giardia. And this is all reference pathogens are kind of all by qPCR, which is not very satisfactory. I'd like to do some cultivation also. We don't know how it goes. If anybody has an idea, I'm always welcome to listen. And yeah, the goal is to identify which one correlates with the health risk and support policy change. So yeah, and controls are important. I'm not going to dwell there. And yeah, so that's was one of the things that's happening right now. What I wanted to do next is so we know that we have high background levels of enterovac. And the question is any from these from sewage? So the approach for that is microbial source tracking. So this NRDC publishes these reports every year. They don't do it any longer, so that's why it's old data. But so these are the. Okay, that doesn't make that's not needed. So it's the closing advisories each year. And what's the source of these closing advisories? And we know the sewage is responsible for closing on this section. We don't really, and I mentioned that epidemiological studies have been on the beaches which have been contaminated by sewage. So we really don't know what the health risk in this section is. There is no real science to support it. Really, we know what's when we have a point source contamination. So that's a big drawback here. So we don't really know where is this enterocoque coming from. And it's important because health risk. So this is health risk. This one, first one, I say, I am going back and forward about this thought. The idea is that this diagram shows the idea that humans can have all these pathogens. Birds only have these two. So humans should have higher health risk. Because it can have all these pathogens, so human sewage have the highest contamination risk. But on the other hand, high levels of ruminant contamination can be also dangerous. So it's yeah. And management, you can fix your problem, the broken pipe, or take the cows away from a stream, or you can also mediate the conflicts. For example, you can have shellfish farm that has sees contamination in the shellfish, and you know if it's coming from the pigs in the forest or is it coming from the sewer lines from the nearby town. And it's also key component actually is this QMRI studies, because you need to kind of identify what reference pathogens you use in that given location. So cultivation-based method often or mostly or always, almost always, don't really tell you where the contamination is coming from. So you can look on the enterocoque, you can look on the phages, they all look same. But if you look on the molecular techniques, they can be different. So for example, coliphages, there are 4 groups of them. 1 and 4 are mostly found in animals, 2 and 3 are mostly found in humans. And you can run qPCR and identify which group they belong to. Yeah. And you can target different. You don't need to just coliphages. You can have Bacteroideales, Methanobrevibacter, all different bacteria, Enterococcus, E. coli, and others. But the idea is all saying that some of the bacteria share, some of the bacterial viruses are distinct for a given animal, and you need to kind of find a way to kind of identify them. So it's the basic strategy is quite simple: site survey, local noise, and historical data case by case basis. You use multi-tiered approach. Single sample has little or no value, and single marker has new values. And you should not try to sell it per sample basis like some people do. And before you start, okay, markers need to validate for local population for specificity, false positives, and sensitivity, prevalence inside the host population, how many dogs, for example, have your marker for dogs. And yeah, so you collect poo samples and then you analyze them. And ideally, you identify also what's the decay rates of your markers are, so you know how quickly they degrade in the environment. And then you verify your ability to discriminate between the sources by blind testing, not tasting. Yeah, so yeah, anyway, so that's what you do. So that's what we did in Hawaii. So what is important, we're focusing on human markers because human contamination is the most, we kind of thought as the highest health risk. That's the basic idea behind why humans. So first we figure out the humans. And human associated bacteroid is high concentration in fecal samples, at least as high as Enterococci, and much less in dogs. So we saw some cross-reactivity with some animals, but one is 10 to the 6, another one is 10 to the 3. We did not find any human polyomavirus because it's shed in urine, and getting infection from the swimming in a swimming pool can be a problem. Maybe somebody wants to study it, but they chlorinate the swimming pool, so that might not be a problem, but it's shed in urine. And urine is not sterile, whatever people tell you. And what else? I just want to show you that it's present in sewage, but not very high concentration, while human fragment, human fecal sample is relatively high concentration. But still the concentration of maybe 1 log or less 1 log or so lower than in mainland. But it's at least as high as enterogocki in the sewage samples. Prevalence. I think I can't remember the human sewage bacteroides, but it's very high. I think there was 10 samples, so 80% for human associated bacteroides. But human papillomavirus, it's usually in literature they say that usually it's between 40 to 60% of people carry it, but more likely in the old age it can be up to 80%. But when you do this, when you try to target cesspools, for example, you might not find this virus. But first of all, it's shared in low concentrations, and second reason is because not all households might carry it, so you might not detect a leak in cesspool by that. And due to the TIO studies, we also looked on how quickly the signal decays. Maybe important thing is, for all these graphs, I don't have really time to explain everything, but there's 2 experiments. One was done only in dark and for 40 days. Another one was a quick one outside in the sunlight. And in the dark, over the 40 days, what you might notice is that superfringence really spores are really resistant to decay. They remain quite high for a long, long time. Another thing you might notice is that there are squares and triangles. One of them is molecular and one is for cultivation. Oh, no. One is freshwater and one is marine water. Human papillomavirus, human bacteroides, they're done by molecular techniques. So the molecular signal decays. It doesn't stay there for 40 days. You can see that it goes down. So it's not like it stays forever. But if you look on here, here we had molecular signal, which is, I think, the translucent one. No, molecular again, human bacteroides and human papillomavirus. Over the 6 hours over the sunlight, they did not decay anywhere. So yes, you can kill quickly in light. Enterogocki, E. coli, and superfringence also, like by the 6 hours it drops down. But if you look on the human papillomavirus or human bacteroides by DNA, then over the 1 day, over the 6 hour period, it doesn't really decay. The DNA is still there. Also, it might be damaged anyway by UV. So that's all that I wanted to show. And I have already showed this one many times, but this one is about microbial source tracking in Manoa stream. So there was 9 sites from Lion's Arboretum down to the Alavai Canal. And so these were the sites. And what we found was that, again, MS1, that side is Lion Arboretum. This one is this Alavai Canal. You can see how the saltwater downstream, saltwater is on site 6. And so what is plotted here? There is E. coli, enterogocki, and superfringence concentration. You can see that. So this level here is the standard for old standard before 130 came. That's I think 100. No, it's 130. 130 standard for enterogocki. So you can see that even Lion Arboretum, the enterogocki levels are above the limit. But when you get to the residential neighborhoods, the concentration could even more up. But superfringence that we don't use anymore was less than 50. That was a superfringence advisory value. It was nicely below that one, but it increased as we get to this middle section. Why it increased? We did got some sewage coming in. So again, this is like just to make a point that this is typical for streams to see such kind of levels of enterogocki. And okay. What happens now? So yeah, okay. So middle section was in violation by both the enterogocki and by superfringence. So both of these are exceeded in the middle section. And these are the markers. So these are the human markers, human bacteroides and viruses. Again, the concentration peak. These are concentration percentage peak in the middle of the stream. So clearly there is human input, but you can distinguish that now using these ones. And we looked on the microbial communities also. We show some sort of decrease in the plankton of the diversity from 4.16 but 2.88. But I must honestly say this idea was completely afterthought. It was and what else was important? There is typical change from beta proteobacteria to alpha proteobacteria. If there still beta proteobacteria exist, they haven't been put together again. And from freshwater to marine environment. And several factors affected the microbial communities like rainfall, pH, conductivity, and salinity. Okay, so there is it's clear, but I think it was showed that three evidence like the indicator bacteria and MSD markers and communities actually showed that, that there is a sewage input and massive sewage leak probably no. And markers really supported that we could use both enterococcus and C. perfringens for monitoring. And otherwise not so bad actually. You saw the numbers went down there because of the dilution by diet. And old sewer lines and illegal cross connections are problem. Okay, so the next thing is the rapid methods. So current methods are slow and current methods are slow, need for rapid notification. So that's what the current situation is when you go to the beach. And what it really means is that wastewater bacteria was detected yesterday and you should have not swum. And water quality might be okay today, but please check our website tomorrow. So EPA acknowledged that issue and made available for the states two methods, 169 and 16011, and provided beach action values. We actually use our beach action value is actually the 130, so it's not actually the same, but was targeted by this one. Anyway, so what is important again, the purpose of these methods is really intended for rapid beach notification purposes. So it's meant as enhancements that state can use to make beach notification quicker. It's not intended to replicate the, it's not intended to replace the cultivation-based methods. Okay, that's really important. That's really to enhance the method, makes it faster, and not to replace. And it's for beach notification purposes. And it's how it's well suited. I think there's several reasons why it's well suited. We see a lot of tourists. We have a lot of beaches with high use and easy to access, and it would make a difference for somebody getting sick. So in California, this has been tested, but it's not really applied to my knowledge. And so you drive to the parking lot and you see the sign, and sign says we tested water quality today. That was the beach that I showed you photo actually. And then you know what the water quality is in these sites. So you collect sample at 7 o'clock in the morning and you can report it by probably 10, 11, if you do it all by electronically. Anyway, so it allows you the same day response, and importantly, it provides improved service to visitors and residents. But people have said methods are complicated. qPCR is not so easy. You need to kind of have all the controls. Technically, there is a lot that goes into it, like standards, controls. It's absolute quantification is hard, and I think, and many states have beaches which are far away, and many beaches have few visitors and cost a lot. And but methods, well, you can't set it up really, so everything is set up for the lab. There was a study done by Squirt where they train people and they learn the method. It's not so hard, and that's definitely not the case in Hawaii. We have beaches close here on Oahu, and yeah, these Hawaii and Alamana, they both have quite a lot of visitors. And if you do it a lot, its probably cost can be decreased the same way. But the problem is that we have enterococcus growing in our soil. So what it again means if we find high concentration on the beach. So we need additional tests. So we did a study in 2013-14. I have been showing the data again already. There's not much new here on this one. So we studied 12 beaches and collected a sample every month. And total 127 samples, and measured enterococci by different methods, MEI, enterolert, and qPCR. And so these are the sites. And find quite good water quality. We had only a few samples. That's the point, kind of like if you want to do epi study in Hawaii, where do you do it if you have 3.1% chance of seeing anything elevated? So it's kind of hard. And only a single sample exceeded both values, the C. perfringens and the enterococcus, so kind of indicating that there is real sewage issue. Anyway, so I put all the graphs here quickly. So this is a comparison of 3 different methods. So 2 cultivation-based methods compared 600 and enterolert, so this is MEI media, and then 2 cultivation-based, and 200 R square 0.8, so index agreement 0.93. And what is important are these red lines and blue lines. So actually, if you look at the 130, so that's the beach action value. Okay, that's the one that you will pull up the beach notification. And it's important, for example, in this section, when you get dots, it means that this method and this method agree. Here again, both methods agree. In these methods, this one will have close the beach, but not this method, okay? And what we find was that actually both cultivation-based and qPCR methods kind of work pretty well together. So I think EPA requires that you're supposed to have R² more than 0.6 and index agreement more than 0.7. So for us, it looks like yes, the EPA recommended method works. And so these are the same comparisons, just how many dots were in this section. So this was 11, did not agree, did not agree. These ones agree, these samples, okay? So yes, okay, so these were the data for that one. So it looks like we can do it, but here's the problem. Around 70% of samples were compromised. It is, so we put this control into the sample and try to detect and see how much it changes, and it changed a lot. It's changed more than a tenfold. So it means that our estimates are tenfold off. The data that I showed was actually combined data from the Alavai canal, and I'm going to get you that. Because most of the samples I could not even use for the analysis.
Can you explain a little more how you found they were compromised?
I'll get to that. I'll get to that, yeah. So 0 point of samples extracted using commercial kits were not compromised. So with all the samples, we did MST and we used it for MST. We looked just to get the viruses off, we need to kind of change the pH, we need to get them stuck to the filter, and we need to get it off. So that's what we did. And okay, and the methodology says that okay, if it's like that, then you should dilute 1 to 10. 1 to 10 did not help either. Still 68% of samples compromised. So it didn't do much of the change if I diluted. So that was my reaction. So I had 1 year of data. I collected all the samples in the freezer. I extracted them, and I started to analyze this batch. All day I go qPCR controls, so and nothing works. That's what I was like. I spent 1 year of collecting my stuff, and now it's all failed. And so I didn't know what to do next. So that's when I told you about the source tracking in Alamana stream. Yeah, so Manoa stream. So I had 1 year of actually the same type of filters, collected same way from the Alavai canal and from the stream. But I only analyzed the first ones from the Alavai canal, which I know that are somewhat salty. So I took these ones that are somewhat salty, and I looked, and interestingly, percent of compromise went down. So that's how I measured the interference for this study is here. So I had a control that I put inside during the extraction. Before extraction, I put the SCADA, like the method says, the control DNA, you put into the reaction, feed it, and then you analyze it. And then you check if you have a clean sample, that's your water, that's the control. You put every sample is spiked the same amount. So your water, the clean one, should come at one time, and when your sample is compromised, if it's not compromised, it should come up same time as this one up. So it should come up same time. So these samples together, they're not compromised. When this is delayed, it means there is something causing them to delay the stuff, okay? It's just a basic test. There's other ways to quantify it, but it's usually it's called like 3.3 cycles, which is tenfold difference. That's you have quite a bit of interference. So I used the word compromise or interference, pretty much the same meaning. So there is interference. I think EPA used the word interference. And so this young lady helped me out. She was a GS student. The question first was it the loss or is it the PCR inhibition? So she seeded samples with into sample, and she also seeded the control into the master mix. And when she did in the sample, the problem occurred only when she seeded the stuff into the sample. It never occurred when she seeded the master mix, okay? So if you put it in the master mix after the extraction, you have no problem. If you put it before extraction, you have a problem. So something is going wrong during the extraction. Somebody who reviewed, yeah, what's different now, those two waters? So the answer is actually on that filter. Anyway, so the different controls, we tried, somebody said that, somebody said for reviewing our figurant application said that we put too little stuff, that you should put more stuff. This is actually a lot of stuff put in. That usually your PCR is somewhere in this range, 10, 100, they come up quite late. And he or she recommended to do it somewhere in this range. It did not make any difference how much you put it inside. You still had this problem in marine samples. But freshwater samples, no problem. We tried also different control, and it did not do anything. We tried to rinse the filter with water. The filter that we saw did not make much difference. It was inconclusive. We tried North Carolina sand, and there was not much. It didn't show so much problem. If you get more realistic concentration of the sand, like here, so this is North Carolina, the interference is not so prominent. There's very little of it, or no. But our sand is none of it, even at lower concentrations. It's kind of hard to measure small volumes of concentration. I think environmental waters are probably much less. Anyway, so and what she found out was when you put when you adjust the pH, you're mostly able to alleviate the problem. So here are the samples from different beaches, and we bring down the pH. It's mostly worked and helped to get rid of the contamination. And of course, Enterovoc are not good enough. So we tried to. So first thing Eduardo was trying to do is to try to show. I have 10 minutes and 40 slides. So Enterovoc and Enterovoc. Okay, what he was showing that if you modify the pH, your method is still workable. And another thing, he was looking also human-associated bacteroides to use as an indicator. But they were not correlated with Enterovoc, which is not surprised because source is different. So he did not see any correlation in his samples he collected from Alavai Canal between the Enterovoc concentrations or the human bacteroides. So here are the summaries, and I saw that one in New Zealand. That's really nice. I wish that would be in Hawaii. You go to I think there is a lot of promise on beach methods, and but I still think that we need an alternative indicator. The Enterovoc is not enough. Okay, so these are and we have submitted this one, but it has not accepted, or I haven't got any reviews back yet. Anyway, so. Okay, that's what I would wish, that's my wish list for Santa Claus. Anyway, small sample volume size. I try to be brief now. So there's a lot of heterogeneity in water samples, everybody knows that. And we actually purchased and we actually received 3 more. We have 4 of these systems in our lab right now. They allow really to filter large volumes. They're all computer controlled. And we went to Kauai. This is DOH Carrie and Tinale GS student. We collected, filtered a lot of water. Yeah, what we found was, yes, if you do the large volume, you're able to, point is this one, large volume, regular sample, you are able to detect much more things with an ultrafiltration than compared to the craft sample. So you have more seeper fingers, positive samples. 1, 2, 3 are the coastal seeps. So you can see the seeper fingers up here. And you can see cauliflower detected on side 4, but that's 3. And human associated marker also here and here. So the 1, 2, and 3 are coastal seeps that are the small freshwater inputs from the groundwater outputs, actually from the groundwater outputs. And yeah, and there is a huge issue here that I have no idea what's happening, but I'm not going to that. This is another test. This is a peppermint motle virus, which has high concentration in our sewage, but we don't know where it's coming from there. Anyway, so here's what I think about it. This provides really good representative sample, but it's labor and time intensive, and contamination issues always also there that's in back of our mind because into bleach the system between the samples, collections, and so on. So it can be tricky. So the groundwater, that's the other stuff that I really want to talk to you today. So we were able to collect 37 groundwater samples. That was the max we could do. I'm sorry for that. And there is really many reasons why groundwater matters. This is just copy and paste, I think, from a research proposal. And yeah, so with population growth that nobody wants to talk about, we're expecting to see more anthropogenic contaminants in our coastal, in our groundwater. And in Hawaii, what Roger told me when I came here was that we don't really know what's living in our groundwater. And we should really have a better evaluation of the stuff, because the only thing that we measure is the limited set of indicators, E. coli and total coliforms in groundwater. And And if something happens to our groundwater, it would be really useful to know what's really, what was the normal state and how it's changing. And it's important in making management decisions also. So this is like, I think, cartoon that's from Portal Photos website. So I guess that we had the basal aquifers wells, which are these deep wells and inclined shaft wells, and we have dike aquifers, which we had tunnel sites. So two types of aquifers, basal and dike aquifers, just simply. There's probably more into it. So these are the sites. We went and we collected water samples. I believe it was 8 liters of water. And what was really amazing for me, at least, I don't know, I have never studied groundwater, so I didn't expect much. But the diversity that was there, it was rivaling really the diversity in the soils. You can say that maybe we contaminated. I don't think so, because what was there was absolutely different what was in soils. And the groups that were there, well, I've never seen anywhere. Like we do sequencing in communities, we have done soils and wastewater and stream and ocean. But there are these interesting groups like Omnitrophica and Parcobacteria and some other really that I have never heard about. So I thought it was really interesting. And yeah, and here are top food line classes. There are the list of them here. You can't read it even, sorry. And what was the what was really like important factors were sulfate, sodium, and nitrates. So we think that there's quite a bit of chemolytic autotrophs. Yeah. And I don't really know how to do AMP based on the 16S amplicon sequencing, just a functional analysis, but we looked on the nitrifiers and denitrifiers and all this. But what is important, so core communities, okay, basal aquifers 0.63%, dike aquifers 0.2%. There's only few groups that were only present that are present in all of the groundwater samples. So 63% and 0.63% and 0.33% of samples were the groups that were there were shared between all the samples. But these ones that were shared were actually very abundant. So that's the sequences that were there. And yeah. And there was quite good groundwater quality in these samples. So we did not see any E. coli, superfingers, coliphages. We did see some total coliforms in the samples. So, but don't get scared. The water gets treated before it reaches you. They usually chlorinate it before it gets, because to avoid the growth in the distribution system. No serious associated markers either detected. So here were the conclusion for these ones. So yeah, the sulfate, nitrate, and sodium concentration correlated significantly with groundwater bacterial community. That was, I think, very important. And the diversity that are also the groups that were there, I think, indicated that it's a large adaptive potential in the Oahu aquifers. Okay, and it was really distinct from everything that I've seen and very, very interesting. But anyway, I have 2 minutes left. So and I can make it. So rainwater harvesting, so there are many people who in Tantalusa and the Big Island and the other Pacific islands that don't have access to the drinking water. So they are left with their own brain to figure out how to get water. So one option is to do rainwater harvesting. And it's not regulated because if it's smaller than 15 household connections, and less than 25 people, there is no regulations that apply, I think. So we did a study there, and you can read about this one, about in rainwater harvesting in American Samoa, yeah. So that's another study. And we also looked on the wastewater. I haven't published, and I have a plan maybe, but it's, we are looking on what's in the raw wastewater. I don't know why Honolulu was so different. So this is the raw wastewater here on these sites. So we collected samples, 3 samples once a week, and when you collect them, when you compare the sewage, people say sewage everywhere looks quite same. And the Honolulu sewage look other than 3 more other plants. But what is interesting, after primary treatment, there is little change. But when you do secondary treatment, of course, you see a change. Primary treatment is nothing less than just settling stuff out. But after secondary treatment, the activated sludge, that's what the typical use. It changes quite a bit. And our warm water as well when you do disinfection steps. But sand damage, of course, doesn't have a secondary treatment, everything clustered together. But what it means is that you have microbial communities associated with Hawaii kai, with Kailua, and with Honolulu, and you can actually go to the coastal waters and actually try to detect them. And currently, so the QMRI is really important for us. Peppermint motrovirus project is I really want to know why we have high concentration in really pristine sections again. I don't know why is that. We study choline lagoons right now. We have a water quality project. I would really like to do more qualifiers diversity this summer. Hopefully we have a real student who can do that. And we have been contributing to other projects like Dr. Reyes, Babcock, and Cooney. And yeah, American Samoa, we kind of try to replicate. Idea is to kind of try to replicate what we have done here in Hawaii. But there are many challenges. So we get samples like that from the city, and we try to answer what is this toxic algal blooms or not. So this ceratophyllum demersum probably not. And so there is many challenges which are probably more like opportunities. So yeah, yeah. Thank you. And I was 1 minute over. And yeah, these are the funding agencies that have supported us. And here are the collaborators and students and postdocs. And I think that's it. Thank you.
Before you head out, if you haven't signed in yet, please do so on the sign sheet. Are there any questions for Marek?
Yes.
Hey, Marek, so you mentioned about the alternative indicator.
Sorry?
Alternative indicator,
Yeah.
for ranges. And your data also shows that there's quite a bit of them in the soil too. So
Shows.
that would end up being the same story as coni and right?
Yeah.
So how do we deal with that?
I have no idea. I don't know why we have so much soils, but yet it seems to work in the streams. There's quite a bit, and that's I don't know. I'm very sure that our estimates are very good because I had a very stupid idea. I thought I can do 16S sequencing and tell the zipper fingers isolates apart, which is stupid. So it shows how little I know. Yeah, I know that the estimates are really good. I mean that we have very precise when we do that. Not very precise. Plus, we have 6% false positives. But I really don't know what to do with them if we have so much in the soils. Which can be a problem, yeah. But maybe the filtration is not like that. I don't know why it seems to be working if we do the analysis in the water and why we have so much in soil. Specific qualifiers look really good, but we had a study actually which I didn't show, which is also microbial source tracking, which was in the, I should know, Kaneohe Bay. And where we had after rain, we had huge numbers of qualiphages in the F-specific qualiphages in the pristine section, which could be birds, but yeah. So maybe F-specific qualiphages are better. I know the EPA is really interested in F+ qualiphages currently. If not, the new standards might come up or criteria with them, but yeah. So I don't have a really good answer what's the one, but I know that LEP in 2011 did this QMRI study in streams and it kind of went unnoticed in many levels, and it clearly showed that C. perfringens is better health risk indicator than Enterococci for Hawaii. So we're trying to do it same, and I thought the best way to do it is to work with EPA and work with BEAM and get advice from everybody to get everybody available. Yes?
Given the lack of ability of indicator organisms, how far away are we from actually measuring the most likely pathogens?
Taoyan might have a better answer. I know that he's doing quite a bit of next-gen sequencing, but I don't really know yet how to do with next-gen sequencing cost-effectively all of them. Because when you do the 16S that I'm doing, my sequencing depth is not enough to distinguish them. And maybe if you do some sort of hybridizations on the chip technology, maybe that will allow you to do it. But you need to quantify it and have all the controls in place. I I don't see how pathogens can be like used daily anywhere within next 10 years. I wouldn't see that any changes. IDEX is so easy for labs. It takes 1 minute to mix reagents together, and then you read next day and throw everything away, and it's done. Yeah, the cultivation-based techniques. Yeah. Did I answer the question, or did I?
Yes, yes.
Any other questions?
Yes.
I was just curious, I'm ignorant, what's creating the high levels in Manoa Stream? In that, that was Manoa Stream you
Yes.
were measuring,
Yeah.
and as you came down in the middle,
Mhm.
they were quite high.
Yeah.
Is that because the sewage system is leaking?
Probably sewage system. I think there is a slow leaks all over the place, because even those streets, I live in faculty housing, and there was 2 years in a row when you walked and you could smell sewage. Then it took like 1 year to fix it. If you look on the sewage line maps in the up there above the Manoa marketplace, they go along the stream actually there. So it's not surprising that it leaks. And its systems are old, and I don't want to blame anyone. The city, I mean, who has money to fix all this?
Yeah.
And it's everywhere the problem. So that's why I put it that it's universal problem. It's like, yeah.
Any last questions? All right, let's thank Marek again. Thank you all for being here. In 2 weeks, we have the next seminar. So keep an eye out for that.
I will send you a copy of